Okay, so let's get started. Welcome. So today let's finish the function call, and next time, and then we're gonna continue to like data. How we can represent data in binary level. So if you remember, last time we were covering, we covered how we can implement the function calls, and we talked about caller saved registers and callee saved registers, and how we pass the arguments and what instructions are involved to make a function call, like a call and return instructions more specifically. So I think now we're gonna see how this recursive functions are implemented in assembly level. So this one will be a true litmus test for you guys whether you actually understood everything correctly. So let's see example recursive function first. So this one is a pop count function we saw last time. So, but it's like a different version. We're doing the same thing in a different way. So if you remember, the pop count function counts. It takes like a 32-bit input, counts the number of ones in the bits, right? So the way it was implemented was take the value of x. You basically compare the LSB, the least significant bit, with 1. And if it's 1, then actually we add 1 to it, and then we shift it by 1 bit, and we also check the LSB again, and so on. We repeat the process until the value becomes 0. And here's another version. Let's understand this function first. So this is pop count, recursive pop count. So it takes it takes the unsigned long integer x as input, and if x is 0, simply it returns 0. Right? Because if you have the number of ones is just 0, right? So you can simply return 0. Otherwise, you basically process it recursively, calculating number of ones of the version of x by 1 bit, right? So you basically this one computes how many ones are there. If you actually shift this value of x by 1, right? It's kind of remaining task, and plus the value of current LSB, right? So if you take end of x with 1, then basically this value will become 1 if LSB is 1. This value will be 0 if LSB is 0, right? So that's basically how this recursive function works. Hopefully you understand this simple function. So let's compile this function, and the code will look like this. This is the binary version of the function. So here, I'm going to explain this code in more in the next slide more detail. So in the first part, so this part is basically corresponds to this red portion in the original source code. So what it does is it simply compare the value. Basically, you copy the value of 0 here to EAX register, and basically you compare the value of the two. Value of this So basically this one is very simple because RDI actually holds the value of x, right? If you remember the calling convention, the first argument is passed through the register RDI. So this RDI actually has the value of x. So what it does is it actually takes end of the two, right? It just takes end to itself. So this computes. This one computes like x, bitwise end x. Right? That's the test instruction. So it actually takes x and x. So if x is 0, then the value will be 0. If x is non-zero, then it will be non-zero because it's simply just the value itself, right? So you do it. And if it's equal, jump equal means if it's 0, then actually it just exit the loop. I mean exit this function call, exit this function. Otherwise, you go into the body of the function, right? So this one is when the value is 0. This is when the value is not 0. Okay, so it's this kind of header of the function. And if you see, there's one, what is this thing, like a ref thing, right? Because you're supposed to have just ret, like return, right? But there's some weird instruction is there, and basically this one is kind of dummy instruction. Don't worry too much about it. It's totally fine. You have a function without this instruction. It's just there for performance, as a performance optimization, because it's kind of like a history, like a legacy. I mean, in some of the old AMD architecture, they actually have some performance problem if there are two jump and return instructions, back to back. So in this case, this instruction is return immediately. Then actually some of the older AMD process doesn't handle this case very well, and it actually causes a huge performance penalty. So it works correctly, it works fine, but the performance is very bad. So prevent that kind of things from happening. The GCC actually inserts some a dummy instruction, this no operation. It doesn't do anything. So this one is no operations, doesn't do anything, but it's just there as a placeholder to prevent this ret instruction coming right after this another jump instruction. Okay, so don't worry too much about it. So it's just optimization. So this part is implemented. So let's move on to the body of the loop, body of the function. So like this. So in this case, what it does is it first pushes the value of RBX. And this one is actually paired with the pop queue here, right? So this one is actually pushed into the stack because this one is so-called co-li saved register, right? So co-li is because it's co-li saved registers. Actually, this value needs to be preserved before it actually returns to the caller, right? So co-li saved register. So co-li saved register, for co-li saved registers, we know that this value will be preserved across a function call, right? So from this function's perspective, this pop count function's perspective, when actually it enters, reaches this point, we don't know. I mean, we don't know what this function does. We don't know the contents of this call. And the processor doesn't know what's happening inside the function call, right? But what it knows is that this value, RBX, will be preserved across this function call from here between these 2 points. The value of RBX will be the same. That's guaranteed by calling convention, right? So what this function does is it uses this RBX register as a backup register, to preserve some value that needs to be preserved across the function call, right? So let's see what's happening. So it first actually pushes the value of RBX to back up the value. And as I said, this value will be restored before it actually returns to the caller, right? Because it's co-li saved register. And in the next step, it actually computes these two values, okay? So in the first case, because now by pushing this RBX, now this RBX can be freely used by this function because we backed up the value of RBX. So this register can be freely overwritten by this function. So it actually used this RBX as temporary register. So in this case, it first move the value of RDX. By the way, this RDX actually has the value of X, right? At this point, right? So it actually copy the value of X. It actually copies the value of X to the RBX register. And then it takes AND 1 to the RBX register. So we do these two instructions. We effectively calculate the value of X and 1 and store the result into RBX register. Okay? So this one actually two computes X and 1 and store the result to the RBX register. And for the second one, we actually use this a shift instruction, shift right. So what this instruction does is we shift this value of RDI register by 1 to the right, right? And we call the function again, right? Because according to our calling convention, the first arguments of any function call needs to be passed through the RDI registers, right? Because we already originally this value actually holds this value of x. By shifting, this register to the right by 1 bit, we actually get the new argument, like x arrow 1, as a new argument for the recursive function, right? And then we finally call the function this. So now we actually, if you actually call this function, this function will calculate the value of p count underscore with the argument x, shifted right by the 1 bit, right? So this value will be computed by this function call, and then when it returns, it actually holds the return value in the RAX register, right? So what it does is, and then as I said, this value of RBX, if you remember, like this one, EBX is RBX, right? So the same thing. So this EBX actually has, or you can think of it as the RBX, the same. The RBX register actually holds the value of, and then this value is actually preserved across the function call because this register is co-saved register, right? And then the return value is in RAX, so we actually add one return value and store the result back to the RAX register, and we pop the original value of RBX because it is called resaved register. So this value needs to be restored before you actually return to the original caller, to the function, right? So this one actually recovers the value. I mean, this one actually adds, performs the add of these two, values, two terms of return value, and then we pop the old value of RBX to restore the original value, and then we return to the original caller. Okay, so this process should repeat until you finish the function. Okay, any questions about how this function works? I mean, why? Go ahead. Hopefully, this one, become clear to you guys, right? Just doing some homeworks and also reading other materials. But please check this example carefully because 컴페어도 돼요. 네, 컴페어를 해도 돼요. 컴페어를 하면 그렇죠. 컴페어를 해도 되죠. 컴페어를 0으로 해도 되겠죠. 그러니까 컴페어를 0으로 해가지고 CMP 그냥 컨스턴트 값 0하고 그 다음에 그 레지스터 값을 비교해서 만약 이퀄로 하면은 그게 이퀄이면 이퀄이고 아니면 아니겠죠. 그렇게 해도 상관없죠. 이건 this is not the only way possible. It's one of the ways you can do it. I mean CMP instruction is fine too. I mean you can use whatever instruction you like. 우리 지금 밤 랩은 몇 명이나 했어요? How many people finished bomb lab so far? I mean, I'm asking TA. Okay, I know at least one of the students actually finished. School board. Oh, okay. So 18 people already finished the bomb lab. Okay, hopefully it's like 1 week from today, right? The due date. So hopefully, if you haven't started, please do it today. It may take a while if you're not familiar with this assembly language in GDB. It'll take some time. So please start now if you haven't. All right, and the kudos to those who already finished the lab. Okay, so let's move on. So here are observations about recursion. So so here we can actually handle this recursive function without any like a special, maybe there's no such thing like a special instruction just for recursion, anything like that. You can easily, handle this like a recursive function using just very general like a function call and return mechanism, right? So we don't really need any special like instructions or special mechanism just for recursive function call. Stack frames, we actually, because if you remember the last time, what you covered, whenever we actually, we make a progress in executing the program, the function actually grows, right? Because you call the function, chain of functions again and again, and there's a chain of returns, right? So as you call the function, the stack grows. Because whenever you invoke a new function, that actually allocates a new stack frame. So stack frame actually grows like this. And then as you return, actually this like a local, like a stack frame will be deallocated or freed. So then, the function, the stack will actually, shrink. So stack frames mean each function call has its own private storage. It actually save register values and local variable and save return pointers and so on. Because these register thanks to these like register saving conventions, these two like instances of function do not step on each other's toe, right? They actually they're separate. I mean they have like separate space so that they do not really disturb with each other, because each function instance actually has its own like a storage. Of course, like an expression is like buffer overflow. I don't know how many of you have heard of buffer overflow. I mean buffer overflow attack. All right, some good to see. So buffer overflow attack is basically I think I explained it during lecture 1 a little bit. So the idea was, because now you can actually have like a stack of stack frames, right? Bunch of like stack frames there. And if you actually have some malicious code, that can actually overwrite some like a random like stack location. For example, like a return address, right? Because whenever you call a function, you store your return address in the stack, right? But what happens if you actually overwrite this return address with some like a random, like a malicious address? Let's say maybe you can call it, make this function returns to the shell command, like a starting address of like a C shell, right? Then actually, what happens is as a result of a function call, you return to it actually gives you an access to the shell, right? And then you can do whatever you want to do with the shell. So that's kind of an example of how, this like a malicious code can exploit this like a stack structure to redirect the program to any like a random location in the system, right? So that's kind of very popular, method of, security like attacks. I mean, how to compromise your system, and so and stack discipline follows call return patterns. If a P calls Q, if P is the caller and Q is the callee, then callee like Q always returns before P. So that's kind of stack relation, right? The last in, first out. That's a stack discipline, right? LIFO. Last in, first out. So when the function that is called the last time always returns first before the caller, right? So that's the stack relationship, and that always holds in this like in the stack of function calls. By the way, this like recursive relationship also works for mutual recursion. So mutual recursion means P calls Q and Q calls P. Then there can be like a chain of like function call. P calls Q and Q calls P. Then there will be like a chain of like a recursion. So it will be like P1 calls Q1 and Q1 calls P2. P2 calls Q2. Q2 calls P3. P3 calls Q3, and so on. Right? There can be like a chain of, instead of like having just a single version of functions, chain of functions, maybe you can actually have like multiple, functions can be involved in this, chain of function calls. And it also works for this like mutual recursion. And especially if you see this like Android or iPhone like a system software stack, there are a lot of, mutual recursion. One function calls another, and they actually call each other. But this is not uncommon, to have this mutual recursion. Okay, here is so summary. This is x86 64 procedure, I mean, you better understand this part of the lecture to do your like lab, I mean the homework number 2. So the important point is again, the stack is the structure to support these multiple stack frames, and each like instance of function call has its own like a private storage to store local variables and save registers and return address and so on. And recursion is handled by normal calling conventions, which is nice. The figure on the right actually shows what the stack structure looks like, what kind of variables or data are stored in the stack. And pointers are addresses of values or on stack or global. I mean, of course, it's of course thing, right? Pointers are address. All right, so this actually concludes the lecture. I mean, this like lecture 6. Any questions about the material we covered today or yesterday? Today or like last week? All right. If there's no question, let's move on. Finally, we reached the last lecture of chapter 3. So this one will be the last lecture for chapter 3. And in chapter 4, finally, we're going to move on to the hardware side. So this one is kind of software. So this assembly language is a language of the computer, the CPU, right? Then the remaining more than half of the lecture will be spent for how we can make efficient FSM that can execute these instructions. Okay, that will be where this what you're going to cover for the rest of the lecture. But before we do that, let's finish the last part of this like machine level programming or assembly language. So how we can represent data, especially today we're going to talk about how we can represent arrays and structures. Okay? If you did like C programming, you know what's struct and what is arrays, right? So let's cover that. So let's start. This part will be covered by in the textbook chapter 3.8 to 3.9, as I said, and then we're going to move on to chapter 4 next time to how we can build this simple CPU that can execute those instructions we learned in this lecture. Okay. All right. So let's start like array allocation. I mean, you probably already understand many aspects of this thing. So I think maybe it can be a review to some extent. Here's array allocation. Here's the basic principle. Let's say you declare an array, and this one is general like a format of array declaration. You actually have type, right? That could be like integer or char, like a character, short, long, double, float. This one is actually type, right? Yeah. So this one is a type. And this is length. So here are examples. Like in the figure, maybe you can declare character, string of size 12. That means you actually have like 12 characters in your array, right? It's going to take 12 bytes because one character actually takes 1 byte, right? So it's like a 12 byte storage, having like a 12 slots for string values. And the second one is int val, like 5. It actually has 5 elements of integers, and each integer takes 4 bytes. So if you actually, let's say this x is what is called base pointer. So base pointer is the starting address of the array, which points to the first elements of the array. Right? Generally, it actually points the array A of 0, right? This one is the x, the address of A of 0. I mean, the first element, the address of the first element. So let's say you have like 5 integers, and the base address is x. Then the next element will start from x plus 4 because integer has like a 4 bytes in size. And the next one will be x plus 8. The next one will be x plus 12, and so on. If you actually have a double type, double is like 14-point value following IEEE 754, which we already learned, right? So 14-point value. So individual like value takes 8 bytes within this bytes, we actually have like a sign bit, exp followed by fraction bits, and so each element actually has 8 bytes. And character, by the way, this is the array of pointers, right? Because we actually have a star here. That means this is array of pointers, and each element actually has a pointer to a character. Because we are assuming like a 64-bit architecture, every address field actually has 64 bits, like 8 bytes, right? So this one is like address 1, this one is address 2, this one is address 3, and so on, right? So generally speaking, so if you actually declare this like array allocation, the array is contiguously allocated. I mean, it actually occupies the continuous like range of address, right? Because it's contiguous, right? The contiguously allocated region of L times size of T bytes in memory, right? So in this case, the L is 12. For example, in this case, L is 5, and the size of T, size of T is, in this case, int, right? Size of int is like 4. So it will occupy like 20 bytes, and so on. So it's that simple. So let's think about how we can access this array. So let's think about, again, the same like array, type T of length L. And array, like identifier L, the name of the array, can be used, as I said, this one can be used as a base pointer, right? The identifier A, like array name, can be used as a pointer to the array element 0 of type T. So as I said, A is equivalent to the address of the first element of array like this, right? The same. So let's do some very simple exercise. Let's say we assume we have like integer array of length 5. So we're going to actually have 5 integers. And the values are 1, 5, 2, 1, 3, which looks like a zip code in the US, especially this zip code of Carnegie Mellon University. So let's say we actually have, we have like reference of 4, val 4, which actually points to the 4th element, actually not 4th element, this is like 5th element, right? Because the index actually starts from 0. So this one will be val 0, this one will be val 1, this one will be val 2, and so on. Then the last one will be val 4, right? Because you actually have length of array length of 5, the range of the index will be 0 through 4, right? So you're going to have like 5 elements. So val 4 is like 3. What will be the value of val? So this one will be this guy. So it will be the starting address of the entire array, right? That's the convention. So we actually, this one's type is like an integer pointer type, and then the value will be x. X is the starting address of this entire array, right? What about x plus 1? Val plus 1. So val is the pointer, as I said. Val is the pointer. If you add 1 to it, that actually returns the value, the biggest starting address of the next element. Okay, so this is basically equivalent to the address of a val of 1, right? Address of val of 1. And, ampersand val 2 is x plus 8 because it actually points to the 3rd element in the array. What is the val of 5? The answer is we don't know, right? Because this one actually refers to the value here, right? Because this one will be val 4, and this one will be val 5. So with this, by this, we are referring to the value of this location, which we don't know. So value is unknown. And this one is equivalent to the accessing the val of 1. So in this case, this one refers to this one. And val plus I is pointer type again. And this one will be computed as x plus 4 times I, right? Because the length of integer is 4. Anything not clear? Anything weird? Does everything make sense to you? Okay. Maybe it's too easy. All right, so let's see how we can represent array in more detail. So let's say we have 3 arrays, 3 integer arrays. Before we do that, we first do the type def. We actually define a new type of gypdig. So gypdig is basically the array type, integer array of length equals to 5. Okay, so there we actually define a new type called gypdig, and gyp is nothing but an integer array whose length is 5. Right? So that's the way how we can define a new array type. And from now on, we can actually use the new type called gypdig. And gypdig CMNew actually which actually have 5 integers 1, 5, 2, 1, 3. Gypdig MIT actually has 5 integers 0, 2, 1, 3, 9, and gypdig UCB 9, 4, 7, 2, 0. So they're like 3 arrays, and it's gonna, as I said, it's gonna take the contiguous 20 bytes in the memory, right? Let's say assume that CMNew actually starts at address 16, and MIT starts at address 36. UCB actually starts at address 56. By the way, these numbers are the zip code for the 3 major CS universities in the U.S. Like CMU, MIT, UC Berkeley. So zipdig CMU is equivalent to declaring int CMU of length 5. As this is basically shorthand form of writing this. So in this case, these 3 arrays are allocated contiguously. This one actually CMU starts at 16 and ends in 36, and MIT comes right back. It actually comes, starts right after this CMU, and the UCB starts right after MIT. But that's generally that does not hold. I mean, in this case, in this example, that's actually true. But generally speaking, this continuity of these blocks are not guaranteed. Maybe there can be some they can be have some a spacing between the two and so on, right? That can actually happen. But in this specific example, we assume these 3 arrays are, occupying this memory space back to back, right? So let's see, how this, array accessing, how this array accessing code is generated by the compiler. So here is a very simple function, like a get digit. So this one actually takes a pointer starting address of the gypdig as input, and also the index, which digit we are referring to. So it actually receives the starting address and the index, right? And the starting address of the array and the elements we are referring to, and actually returns the value, the digit, at that location. So if you call this call get digit with CMU, and let's say it's 2, then the return value will be actually 2, right? Because this one actually sends the starting address of this array as first argument, and 2 as second argument. This location a array element 0, 1, 2, 3, 4, basically return the value of CMU 2. You should compile. By the way, this is typo. This is not IA32. This one is x86 64. IA32 is a 32-bit Intel architecture, like decades ago. So it's kind of old. So, but we are assuming a 64-bit architecture. So this one must be x86 64, 64-bit version instead of 32-bit version. So get digit, the first argument is passed through RDI register, and second argument is passed through RSI register. The first register, RDI, contains the starting address of the array, in this case, the Z, the CMU maybe. And the second register, RSI, contains the array index. So how we can calculate the desired digit, the pointer to the location we are referring to? So generally speaking, the address of the memory location we want to access is the sum of the base address, the first argument, like sum of the base address plus 4 times RSI, right? Because generally we need to actually scale each element actually takes 4 bytes. So in this case, this one actually takes 4 bytes. This one takes 4 bytes. So generally speaking, if you want to access nth element, the location, the starting location of the elements will be the base address plus n times 4, right? So so desired digit is available at RDI plus 4 times RSI. Okay, and you can usually simply using simple memory reference format using parentheses. So if you execute this instruction like move-l RDI RSI 4, then basically what it does is it actually accesses the value at the memory location of %RDI plus %RSI times 4. Right? It actually reads the value from the memory, from that location, and copies the value to the RAX register and returns, right? That's simple. What about, let's take a look at a loop example. Let's think about, this simple loop. It actually received the starting address of the array as argument, like a z. Z is the starting address of a zip dig, which is a 5-entry an integer array. And we actually enter the loop, and we increment the value of individual elements by 1. That's what this simple looper does, and there's no return value. That means it's very simple, very, very simple loop. So let's start with, this part. It first tests. You already know how we can transform this for loop into assembly, right? We already covered that part. So it first tests. It first actually initialize value of I to 0, and it jumps into the middle. Okay, so it actually first initialize value of I to 0. That's kind of initialization, and it moves to the jump into the middle to test the condition, because this part is basically testing this this condition, right? Whether it's satisfied or not. So it first check whether compare the value against with 4, because GLAN is 5 in this case, right? So GLAN is 5, so we actually compare the value with 4. If the value is less than or equal to 4, then we go back to the beginning of the loop. Otherwise, we simply fall through to the return instruction. Okay, so that's what's happening here. So you pass the test, meaning that because initially this I is 0, so we actually compare the value with 4, then I is actually less than 4. So we go to the header of the loop, and then in this case we add 1 to the memory location, point to by this tuple RDI RAX4. So the computed address is RDI plus RAX times 4, right? That's the address. So what it does is it adds constant value 1 to the value in the memory location, RDI plus RAX times 4. That's what's happening, right? And then store the result back to the memory. And we also increment the value of RAX, because this part is executed by this line. We increment of RAX by 1, and we do the same thing again. We actually compare the value against 4. If it's less than or equal to 4, then actually we go back. Otherwise, we just exit the loop. So the takeaway here is that this one can be very this array access can be very easily implemented using a single instruction, right? It's very compact, right? It just takes one instruction. So this actually gives very compact code. And this one is actually very different from what is called like a RISC architecture. Sorry. So I actually explained a little bit about like a RISC and CISC in the lecture 1. So CISC architecture is a complex instruction set architecture, and RISC architecture is the opposite, like a reduced instruction set architecture. And x86-64 is an example of a CISC, like a complex instruction set. So complex instruction set, single instruction is more capable. I mean, it can do more thing with like a single instruction. But in like a typical like RISC instruction, it actually takes like a more than like one instruction to do the same thing. Okay, but you know, in RISC architecture, they can do this like a simple instruction a lot, you know, faster. Okay, so that's kind of trade-off. Whether you're gonna do like fewer instruction slowly, or you actually execute like a more instruction fast. That's kind of, it's not obvious which one is a better approach, because you know, you generally have to execute like a fewer instructions, but individual instructions actually takes longer to execute. Or you know, in RISC side, you actually need to execute more instruction, but individual instructions are more like simpler. So it's kind of design choice, right? And if you actually use like a RISC architecture such as ARM, like MIPS, or you know, Spark, all these things, then actually it usually takes more than one instruction to do the same thing, like to do this. But in this example, as I've shown you, you know, this like a single line of C, like a C statement, is translated into just like a single, like one instruction, right? Which is really, I mean, compact. So let's move on to a more interesting case of a multi-dimensional, like a nested array. So here, like a declaration, like again, we have type and array name and row and column, like a two-dimensional array, right? Then, you know, it's like a two-dimensional array of data type T with R rows and C columns, right? And the type T elements requires K bytes. Let's say this is the assumption. You know, let's say each like elements of type T requires K bytes. So if it's integer, like it's K, you know, K will be 4. If it's character, it'll be 1. If it was double, then the K will be 8, and so on, right? Then what will be the total like array size? Total array size will be, you know, the dimension of row, dimension of a column multiplied by the length of individual element, right? So if you actually multiply them all, that will be the total array size. And then the question is, our memory is basically it's a linear space, meaning that it's like a one-dimensional space, starting from 0 to like f, or something like that. It's like one-dimensional space. Then how we can map this like a two-dimensional space, or generally like a more than two-dimensional space, into like a one-dimensional space in memory, right? That's kind of question. And in C, I mean, in like a C language, or generally actually true for any other language, we actually take like a low major ordering. So low major ordering means that if like a two-dimensional array, something like this, then we actually put this one first, this first row first, followed by the second row, followed by the third row, and so on. Okay? Then what's the opposite to row major? So the opposite of the row major is column major. In a column major ordering, you actually place first column like this first, followed by the second column, followed by the third column, and so on, right? But in our like we usually take, you know, row major, because, you know, it means that row index is the first index in your array. Okay? So if you see, if you have integer array A of R and C, then this one will be the first column. Let me go back to this color. This one will be first column, first row, and this one will be second row, and this one will be n minus 1. This one is nth row. Actually, this is not nth row. It's rth row, right? So that's how you lay out this structure, flatten structure, and put it in the one-dimensional like a memory space. And the total like amount of storage necessary to store this like two-dimensional array is 4 times R times C. Okay. So here is like a nested array example. Let's say you declare an array of zipdig. By the way, zipdig itself is like one-dimensional array, and you declare the array of zipdig, meaning that now you actually have two-dimensional array, right? So you can actually store like a multiple zip codes, and basically this one is PGH0, and this one will be PGH1, and this one will be PGH2, and this one will be PGH3. So if you take a look, this is how this two-dimensional array is laid out. So the first column of the 5 integers will come first, like 1, 5, 2, 0, 6. So this one actually takes 20 bytes, followed by the second one. The second row actually comes the next. So this one also takes like 20 bytes, and so on. Okay, so that's basically how you lay out this structure, this array. And zipdig PGH4 is equivalent to integer PGH4 because it's two-dimensional array of integer. And variable PGH, let's think about variable PGH. This one is an array of 4 elements, right? This one is kind of array of array. This is array of array. So this one actually, it actually has 4 arrays in it. And these 4 elements are allocated contiguously because this one is allocated contiguously. And each element, this is element, right? Each element itself is an array of 5 integers. It's also allocated contiguously. Okay, so it's kind of very natural representation of this two-dimensional array. Again, this is row major ordering of all elements in memory. Okay. So let's think about how we can generate code for accessing like a nested like array rows. So let's say we actually have like a row vector. Let's say A actually is two-dimensional array. Then dimension is like with R rows and C columns, and individual element is integer because now we actually have two-dimensional integer. And A of I, if you only have like one index, A of I is actually an array, right? A of I is an array of like 5 elements. It's an array of like a C element. In this case, C is like 5. Array of C elements. Array of like in this case is 5, right? So A of I is array of like 5 elements. In the previous example, like in zipdig, and each element of type T requires k bytes. So the starting address of A of I. So let's say if you want to access like ith element, then the starting address of this address, starting address of A of I will be computed as A plus I times C times K, right? Because there will be C elements like this, and each element actually takes k bytes, and they are contiguous. So if you want to actually access the starting address A of I, then you can compute it by add like I times C times K to the base address A. Then actually returns the beginning address of A of I, like this one. Okay? And of course, in this case, K is assumed to be 4 because we are assuming like an integer array. Each integer takes like 4 bytes, right? So here's let's think about this function. So get PGH-zip. So what it returns is the starting address of ith element of the PGH array. So if you remember, the PGH is it's a two-dimensional array, two-dimensional integer array. Because if you actually have only one index, that actually returns the starting address of the array, like the element array, right? So if you want to compute this, let's say we actually have 4, PGH actually starts here, and if I is 0, then it will actually index, it will return like this address. If I equals 1, then it will return like this address. If I equals 2, it will return this address. And if I is 3, then it will return this address, right? That's what this function do. So, let's say RDI, actually holds the value of index, then how we can calculate it? So generally, you want to actually return the starting address of row vector. So PGH index is an array of 5 integers, and starting address can be calculated as PGH plus 20 times index, because this one is the multiplication of C times K in the previous slide, right? C is how many elements are there in individual elements. In this case, C is 5, and K is how many bytes it takes a single integer element. So in this case, 4, right? So this is the length of this individual element. This is 20. This is also 20, and so on, right? So if you want to get the starting point of PGH of I, like index, then you can actually return PGH plus 20 times index. So if you generate the code, it will look like this. So it actually uses like an ADA instruction, load effective address. It computes the value of parentheses RDI, RDI4. Then what it computes is percent RDI plus 4 times percent RDI, right? So if you add them up, then this one will be like a 5 times RDI, like 5 RDI. And then in the second instruction, you add this value and scale it by 4. So if you actually scale it by 4, this one will be like 20 times RDI, which is RDI is actually like an index, right? 20 times RDI plus the base address PGH. You add like this number to the PGH. So the value will be PGH plus 20 times index. And you store the result to the RAX register. Okay? So it actually takes like 2 instructions to calculate the starting address of the PGH. Basically, you get this number. All right? So to generalize, if you want to, let's say you want to actually access like a specific element, like this. In the next slide, like this. So note that, in this case, you actually returns a specific digit of zip code, right? In the previous example, like 2 slides ago, in this example, you actually returns the integer pointer, which is the starting address of this zip code, right? So the difference is, in this case, you return like integer pointer, and in this case, you actually return integer, like this value, right? So in this case, it actually receives 2 input parameter, index and digit. So index actually specifies, which zip code you are referring to, among this like a 4 zip code, which one you're referring to. The first element, the first argument actually refers to which zip code. And arguments dictates, which digit you're referring to. So if you actually use like this index and dig, you're gonna actually you can actually pinpoint the exact digit of you want to access, and actually it returns the integer value from the memory location. Okay. So if you want to access the specific like memory location and the value of the location, then PGH index dig is actually integer type, because we are not talking about the specific value in the zip code. And the address for this value is computed like PGH plus 20 index, because this one actually returns the starting address of the specific zip code we want to access, right? And then this dig, this actually within this like zip code, this one actually gives us the offset to the digit we want to access, right? So individual like this like a digit actually takes like 4 bytes. So if you actually want to access like second digit, like a third digit, then this one will be value of 2. So now we're going to access this one, right? So the address is calculated is PGH plus 20 times index plus 4 times dig. And if you take the common term, like a 4, then pgh plus 4 times, 4 times index plus dig, right? You can simplify like this. And then using this formula, we can actually generate the code. Generate code like this. So first, we compute, 5 times index using like a load effective address instruction, area. If you remember, this area instructions only computes this part of the address, but it doesn't really access the memory. It only computes to do the arithmetic, to calculate the pointer, and then it stops. I mean, just simply store the pointer to the register, but it doesn't do any real like memory access. That's the difference between move and area, right? So it actually computes the value of this RDI4, then it actually now index value, and then we add this RSI value of RSI register to this value. Then it will be sum of, because the RSI register holds a second argument, which is dig. So now we compute 5 times index plus dig and store it into the RSI register. Finally, we access this memory location, pgh plus RSI times 4. So it will be the effective address will be pgh plus 4 times 5 times index plus dig. And then we actually access this memory location and get the value, copy the value to the EAX register by the move instruction, right? Kind of simple. And I want to compare, this one with like a multiple array example. So multiple array and two-dimensional arrays are different. So here's a multiple array example. Let's say we actually declare 3 one-dimensional array. So all of this, like this is like a 3 one-dimensional arrays, right? So now we actually have like 3 arrays, right? There's no guarantee of contiguity in this example, right? Maybe these like CMU, MIT, UCB arrays are maybe disjoint. I mean, they are kind of not contiguous. They may not be contiguous, right? So there are, in the memory space, let's say you have a memory space like this, then maybe CMU is here, and maybe MIT is here, and maybe UCB is here, something like that. They don't have to be contiguous. Maybe they're replaced some like a random location. So if you actually have like 3 like a one-dimensional arrays, and then now you declare the array of integer array, array of integer pointers, right? So this one is univ is array of integer pointer, right? So each element actually stores a pointer to an array, right? And we actually have like a three elements. And then this univ actually has like an array of integer pointers. It actually has 3 elements. So these there are 3 pointers, like this one, this one. And these 3 pointers actually points to the 3 arrays we declared in the previous pane. So the first one is MIT. So MIT actually it actually points to MIT array, and the second one points to CMU array, and the last one actually points to UCB array, like this. So the difference between the previous like a 2-dimensional array is that there's no guarantee of contiguity, right? In the previous like a 2-dimensional array, they look like this, right? They are located in the contiguous memory space, like continuous memory space, right? But in this case, these 3 arrays are kind of placed like disjointly. I mean, they can be anywhere. And then these like 3 pointers actually points to the beginning of individual arrays. This is called like a multi-level array. Okay. So let's think about how this multi-level array, how things gets different. So variable univ denotes array of 3 elements. Each element is pointer to integer array. Each pointer points to an array of ints, right? That's basically how this multi-level array is constructed. So let's think about, do the same thing as we did for 2-dimensional array access. This is element access in multi-level array. So, this get univ digit. So now, we want to access the specific digit and receive the integer as a return value. It takes the index and digit, and we want to actually access the specific digit like this. Okay? Then, we want to first compute the location, the address of this thing, right? And, we must first access the starting address of individual array. Let's say index actually gives us the array, right? So if you actually have like univ index, then this value will give us a starting address of one of the three arrays, right? So this one is the pointer to one of these three addresses, either this one or this one or this one, right? And then if you actually have like a second element, like a ditch, then this one actually points to a specific integer elements inside the array, right? So what we need to do is we actually have to first compute the beginning address, this, and then we add like a 4 times digit offset to that like a starting address, right? Then that gives us the exact location of the specific integer element we want to access, right? So here is the code, how it works. So it first, by the way, it actually accesses like this value. Okay, so this part, mem like univ times 8 times index. This one actually gives us the value of univ index, right? The starting address of the integer array, right? And then we add like a 4 times digit to it. Then actually it gives us the specific like a location in that array, right? And we want to actually access the value in that location. So if you want to compute this, so here is the code. So the digit, the second argument, is shifted left by 2, meaning that we actually multiply the value by 4, right? Because we shift left by 2, which is equivalent to 4 times digit. And we add the value of univ and multiply by RDI times 8. So this one will give us the, so this part computes this one, right? So univ RDI 8 returns us the sum of univ plus 8 times index, right? And then we add the value in the memory, like because this one actually accesses the memory. So value in the memory plus RSI. RSI is 4 times digit. So if you execute this instruction, the final value stored in RSI will be univ index plus 4 times digit, which is the exact location you want to access, right? And then we use this address as pointer. We can actually move the value here, this in the RSI, pointed to by the RSI register to the EAX register. So this one actually loads the value into the register, right? And then we return. So that's how this code works. I mean, this function is translated into the assembly code. Okay. So let's compare the two. So if you remember, we actually had like this dimensional array, and this is multi-level array. Let's compare the C code. So in both cases, we want to access the specific elements in the 2-dimensional data, right? So it actually takes both index and digit, and then it returns the integer value from the specific location within the zip code, like this place or this place, something like that, in both cases. And they look almost exactly the same in C code, right? So in the C code, this one actually looks very similar. I mean, this one looks like, almost the same. You cannot really tell the difference between the two by inspection. So although accesses look similar, but their address computations are very different, right? Because in this case, we want to access, the address will be like this, there's like a base address, like a PGH, which is like a base address for the entire data structure, plus 20 times index plus 4 times digit, then we can actually pinpoint exactly which digit you want to access. This case is much more complicated. So we want to first access this univ array to get the beginning address, starting address of one of these 3 arrays, and then we add offset to it. So in this case, it only requires like one memory access to get the value, right? But in this case, we actually need to have like 2 memory accesses. The first one to get this like a starting address of one of the 3 arrays, and the second one to actually get the digit. Okay, so that's a difference, kind of subtle difference between the 2. So here's like an n by n matrix code. Even though you write similar code, their actual like internal representation may be very different. So here are like 3 representations for n by n matrix. So the first one is kind of most like static. I mean, static means everything is determined at compile time. I mean, before you execute the program, right? So in this case, you actually have constant, like n is 16, and you do type def. You define a new type of 2-dimensional integer array, like a fixed matrix nn. That means when you actually write the code, your dimensional matrix is already fixed to 16 by 16 in this case. And compiler already knows it. Oh, compiler knows, it's 2-dimensional array with like a 16 by 16 dimension, right? Then if compiler already knows it, it can do a lot more optimization using this information, right? That's the fixed dimension. So know this value of n at compile time when you compile the code. Okay, what about this case? Variable dimensions. So let's think about, in this case, you only pass a pointer of integer. Then in this case, you don't really know what's the dimension of this array, right? It only is simply just point to the starting address, but it doesn't give you any information about the size of the array. Is it like 1-dimensional, 2-dimensional, 3-dimensional, or is like what's the entire like length of the array? We don't really know using this code. So in this case, we explicitly give the index function like this. So actually, this one actually defines the index. In this case, n is the column size. I is the row number. J is the column number. So we want to, let's say we want to access A of I and J, like before. But because we don't really know what's the size of a column, how many elements are there in a single row, we don't really know, right? So this one is given as a parameter, like n. So n is basically the width of your array, right? The column size. In this case, it explicitly computes the index by I times n plus j. Okay, and n is variable here. So n is kind of determined at runtime. It can be, can be 16, could be 30, could be 256. It's actually fixed. It's determined at runtime, and when you actually run the program. So this one is a very traditional way to implement dynamic arrays. Dynamic arrays, basically, you declare this array at runtime, not at compile time. The dimension, depending on your input size, you may actually need like a large array, or you may need like a smaller array, depending on your inputs, right? And then you basically declare the right size of array, like using like a malloc or some like a dynamic like memory allocation call. And this one is kind of traditional way to implement like dynamic arrays with like a variable size determined at runtime. And also there's like a third option, which is called like a variable dimension. Again, like this is a variable dimension, but implicit indexing. But now you can pass now GCC support this kind of indexing too. It's not really standard C, declaration, but GCC actually support this. What it does is you actually declare this int as an array. N is variable here. N is actually determined at runtime. N is not fixed at compile time. So if you actually declare this int as like nn, then the compiler knows, oh, this n is the dimension. Okay? And then it generates the assembly code by taking this information into account. And you don't really need to provide this like explicit like indexing function anymore. Okay? This part is handled by the compiler itself, and you can simply use a of I and j. But the difference between these two, this one and this one, and in this n is like constant. This small n is variable. Okay, constant is declared at when you actually write the program, and variable is the value of variable is determined when you actually run the program, right? So here's like a 16 by 16 matrix axis example. So let's say we have this is example number 1. I've shown you like 3 different cases. It's case 1. So in this case, let's just see column size is 16, and each element take 4 bytes. Then if you want to access like I and j and fixed matrix size, the size of matrix is already fixed at compile time, then it actually does, the address is calculated in this way: a plus I times c times k plus j times k. That's the exact, the location of the exact digit you want to access. And you can actually use like a shift instruction to, compute 64 times I and add like a to it. And then now you get like a plus 64 times I. And then you scale it and add a base address. And then you can actually access this address. Like if you plug in 16 and 4 here, it'll look like this. A times 64 I plus 4 times j. It actually takes like 4 instructions to execute this program. But if you actually have like n times n array elements, let's say n is a variable, then we don't really know the size of the array, right? So we actually have to use like a generic like a integer multiply, because we don't really know the value of c in this case. So in this case, we already know the value of c here and value of k already. But in this case, we don't really know value of c. This value of c is like n, which is determined at when you actually run the program. So in this case, we cannot avoid using this general like integer multiply, because we have to calculate the value of n times I, and we use this LEA instruction to calculate value L times n times I. And finally, we use this move instruction to a times 4 times n times I. So they actually look similar. I mean, they actually use the same number of instructions as previous slide, but the difference is, this like a shift instruction is actually much cheaper than this general like integer multiply, right? Because we don't know exactly what the size of array. We actually cannot avoid using this generic like integer like a multiply instruction. But in the previous example, we actually we can actually use like a fixed like a shift instruction, because we already know the size of the array. All right. So actually time is up. So I'm gonna actually stop here, and I'm gonna cover the structures next time. I'm gonna move on to chapter 4. And if you have any questions, feel free to ask me. Otherwise, you're free to go.